watch this. A real frontier AI model, GPT 5.3, is processing requests at unprecedented scale. This isn't running on a generic GPU farm. This is the hardware war nobody expected. NVIDIA's Blackwell B200 versus OpenAI's purpose-built Jalapeño ASIC. NVIDIA's Blackwell B200 GPU is a behemoth, built on a dual-die GB100 design packing 208 billion transistors. It features a massive 192 GB of HBM3E memory, delivering up to 8 TB per second of bandwidth. This memory architecture is critical for accommodating large language models, allowing a full 70B parameter model and FP16 to reside on a single GPU. The B200's native FP4 path is a significant architectural leap. Its second-generation transformer engine provides 9,000 teraflops of FP4 tensor performance. This halves memory usage compared to FP8, effectively doubling the model size a single GPU can serve or allowing for dramatically larger batch sizes, directly impacting inference throughput for large LLMs. OpenAI, however, unveiled Jalapeño on June 24, 2026, a custom application-specific integrated circuit. Co-developed with Broadcom, Jalapeño is not a general-purpose accelerator. It is specifically designed from scratch for large language model inference, optimized for OpenAI's roadmap including GPT 5.3 Codex Spark workloads. The first architectural wall faced by hyperscalers is memory capacity. H100 GPUs with 80 GB HBM3 struggled with larger models. Blackwell shatters this with 192 GB HBM3E on the B200, allowing 70B parameter models and FP16 to fit entirely on one card, eliminating complex tensor parallel sharding across multiple GPUs. The second wall is memory bandwidth. Even if a model fits, data starvation bottlenecks inference. The B200's 8 TB per second bandwidth, a 2.4x increase over H100's 3.35 TB per second, ensures data moves fast enough to feed its tensor cores, sustaining high throughput even at batch sizes where previous generations would stall. Jalapeño, conversely, tackles these challenges by hardwiring LLM logic into silicon. This allows it to strip out extraneous training logic, focusing solely on inference efficiency. Broadcom's silicon implementation expertise, coupled with OpenAI's deep model insights, enabled a rapid 9-month design-to-tape-out cycle, partly accelerated by OpenAI's own AI models. Performance per watt metrics become paramount for hyperscalers operating at gigawatt scale. Early testing for Jalapeño indicates substantially better performance per watt than current state-of-the-art general-purpose GPUs, with claims of roughly 50% lower cost and 50% better cost efficiency, though specific benchmarks are still pending public release. The third wall is thermal dissipation. The B200's TDP of 1000 W, configurable up to 1200 W for liquid-cooled versions, represents a significant increase over the H100/H200's 700 W. This mandates advanced cooling infrastructure. Air cooling is largely insufficient. Liquid cooling is now mandatory for Blackwell deployments. A single GB200 module, integrating two B200 GPUs and a Grace CPU, dissipates up to 1200 W. A full NVL72 rack, containing 72 B200 GPUs, generates over 120 kilowatts of heat, necessitating direct-to-chip liquid-cooled plates and rack-level liquid-cooled solutions. Jalapeño's purpose-built design aims to mitigate these extreme thermal loads by optimizing power consumption from the ground up for specific inference patterns. While direct cooling specifications are not public, custom ASICs inherently target maximum efficiency at a fraction of the power cost of general-purpose GPUs for their designated tasks. Hyperscalers are increasingly abandoning general-purpose GPUs for frontier LLM serving. Inference now accounts for 60 to 80% of AI compute spend. This cost pressure, combined with NVIDIA's 75% plus gross margins, incentivizes giants like Google, AWS, and Microsoft to invest billions in custom silicon. The strategic trade-off is clear: flexibility versus efficiency. GPUs like the B200 offer broad applicability across diverse AI workloads. Custom ASICs, exemplified by Jalapeño, sacrifice this flexibility to achieve 3-5x better performance. But for specific, high-volume inference tasks? One major drawback of custom silicon is the CUDA lock-in. Existing inference stacks, built on libraries like the LLM, Flash Attention, and TensorRT LLM, are deeply tied to NVIDIA's CUDA ecosystem. Migrating to ASICs often requires rewriting the entire inference stack, potentially taking weeks of engineering effort and locking into a specific cloud provider's SDK. NVIDIA's counter-strategy involves NVLink fusion, opening its interconnect ecosystem to third-party chips. This aims to integrate custom CPUs and ASICs into NVIDIA's rack architecture, making them complementary rather than competitive. This enables continued GPU presence for training and general workloads while ASICs handle predictable inference. The post-H200 era is defined by this architectural bifurcation. High-end GPUs like B200 dominate training and versatile inference, leveraging FP4 and massive HBM3E. Simultaneously, purpose-built inference ASICs like Jalapeño are capturing hyperscaler internal inference at scale, driven by extreme cost efficiency requirements. This shift is not a niche trend. Custom ASIC shipments are projected to surpass GPU shipments by 2028. OpenAI's Jalapeño, with its focused architecture for GPT-5.3 inference, represents a critical development in this ongoing hardware war, promising lower latency for interactive LLM products at scale. The battle for LLM inference hardware is fundamentally reshaping the AI infrastructure landscape. It's a race for peak efficiency, lowest cost per token, and control over the full stack, driving innovation from generalized powerhouses to hyper-specialized custom silicon.